let me switch to the actual introductory talk. And this talk is entitled, What is Quantum Nanoscience? And I want to start with another example. What is a quantum material? Right? I've asked many, probably have asked many of you, what do you think is a quantum material? Well, one way you can find out is you can go to Wikipedia. This is how normal people find out what something is. And you can look at the definition. And let me read it for you because it is so painful. Okay? Quantum materials is a broad term in condensed matter physics to put under the same umbrella materials that present strong electronic correlations and or some type of electronic order such as superconducting magnetic order, or materials whose electronic properties are linked to non-generic quantum effects, that's an awesome term, such as topological insulators. So topological insulator is a non-generic quantum effect. Dirac electron systems such as graphene, as well as systems whose collective properties are governed by genuinely quantum behavior, such as ultra-cold atoms, cold excitons, polaritons, and so forth. A common thread in the study of quantum materials is the concept of emergence. I mean, this is about the most horrible definition of anything I've ever seen, right? It means everything. It has no meaning at all, right? For example, the word quantum, there is generic quantum effects, and then there are genuinely quantum effects. Well, we don't know what that means. Does anybody have any idea what that means? Right? So that's really crazy. Now, the question is it important to define a research topic? Right? And I would argue it is important to define a research topic so that you can avoid something like this. Okay, so how do we go about defining what is quantum nanoscience? What we did almost exactly 1 year ago, we invited some experts from different fields, which I thought at the time might be quantum nanoscience, to come here. Several of them are speakers at this conference as well. A couple of them, few of them are actually on my advisory board as well. And you see there's only myself representing scanning tunneling microscopy, right? So this was not supposed to be what do I want to do. This was really what is this whole field. And it was a really interesting workshop led by our chief operating officer of our center, Michelle, who is actually a professional mediator, not professional leader of those kind of meetings. And it was a 2-day meeting, I think, and the first part of that meeting was nobody had any agreement and nobody felt that we could ever come to some agreement. But in part to her help, we came to a tangible conclusion and we actually made a definition of what do we think is quantum nanoscience. So, obviously quantum nanoscience is a combination of quantum science and nanoscience, that's obvious, right? But what does that mean? You know, remember what I told you in quantum materials? There is no definition of quantum if you want. But we came up with a definition and we thought that it should focus on what we call the modern aspect of quantum. So the concepts such as superposition, entanglement, quantum coherence, quantum measurements. Not just everything is quantum, but the more interesting, I would say, quantum effects. And on the nanoscience, we didn't really come to a really good conclusion which part of nanoscience should be included. But we, of course, we have top-down assembly, such as quantum dots and superconducting devices. And we have bottom-up assembly, molecular nanoscience, controlled defects, and quantum surface science. So there are many aspects of nanoscience that we believe flow together into quantum nanoscience. But the most interesting aspect that we came up with is that we believe quantum nanoscience has at its core the drive to find quantum coherent functionality, to really use these concepts of superposition, entanglement, and quantum coherence to do something interesting, right? To utilize these effects for better sensors or for studying some quantum systems that you couldn't study otherwise, right? Possible applications could be quantum computing, quantum simulation, quantum sensing, but it's not about the applications as much as it is about the drive to actually use these quantum coherent effects in this research field. Now, this is a relatively small community. Many of those key players are here at this conference, but we also believe that developing tools, making devices, exploring the quantum behavior, and making better materials are part of quantum nanoscience if, and only if, they have the goal to go towards quantum coherent functionality. Right? So that is our definition, and of course we went to Wikipedia and we updated an equally bad definition that was there before. So this you can actually find on Wikipedia. So let me give you examples of this to illustrate what we mean by this. So the first one is, of course, in some definition, everything is quantum, right? Molecular orbitals in a molecule, or electronic states in a thin film device, they're all quantum effects, thickness-dependent effects in a semiconductor, right? Is this quantum nanoscience? No. This is not quantum nanoscience because it does not use these quote-unquote new concepts of quantum, such as superposition, entanglement, and quantum coherence. So we all agreed that this stuff is not part of quantum nanoscience. What about a few more examples? So here we have an example. This is a FinFET silicon transistor current technology that you probably have in your computer or in your phone. Undoubtedly, the length scales here are nanoscale, right? They're in the few nanometers to tens of nanometers. Quantum effects play an actually important role in these devices, and that is mostly a negative effect, namely you get leakage currents that are due to quantum tunneling because the devices are getting towards the atomic scale. Is that quantum nanoscience? We believe the answer is no, because that is not a quantum coherent functionality. This is just trying to get rid of quantum effects that you can't avoid. Okay, not quantum nanoscience. But of course, in the same geometry, you can have quantum coherent functionality, right? We can make, other people can make, for example, two-dimensional electron gases and then confine these two-dimensional electron gases with gates on top. At first, in this field, they basically saw discrete transports or discretization of the charge, probably not quantum nanoscience at that point, but nowadays, confining electrons in these puddles is one of the hallmarks, I would say, of quantum nanoscience. So here's a paper taken by Andrew Jurak, who's giving a talk in this session a little bit later. So these are electrons confined to a silicon little puddle, and then you can do coherent manipulations such as these Rabi oscillations of these electrons in this quantum dot. And you see you have here quantum coherence times T2 star of about 100 microseconds and T2 echo of 30 milliseconds. And you can do gate operations very fast, as you can see here. So you have a lot of quantum coherence, and there is a big field developed around these lithographically defined quantum dots. This is a top-down kind of procedure. So this definitely lies in the heart of quantum nanoscience according to our definition. So let's look at another example. Defects, point defects in materials, right? The entire silicon or semiconductor industry relies on controlling point defects to make dopants and acceptors and donors and to control the band structure of materials such as a p-n junction. Now, that's not quantum nanoscience, again, because we don't see any quantum coherent functionality in this. But that same field, the same field of controlling these point defects in materials, of course, here's an example of putting individual phosphorus atoms into silicon, is of course part of quantum nanoscience. So this one here, for example, has been used to do 2-qubit exchange interactions, a quantum swap operation between these qubits or these defect states confined in the silicon device. Right? So that's clearly at the heart of quantum nanoscience. So it really shows you that there's an intent to utilize this quantum coherent functionality in quantum nanoscience. Right? So another example, molecular magnets. We have a session in this conference on this. So maybe at first, magnetic bistability in a metal-ion cluster. Roberta is actually here. One of the co-authors of this paper was a fantastic work, right? You now have a giant spin, S equals 10. You can maybe use it for data storage. It's a fantastic work. Then people, including Roberta and also Wolfgang Wernsdorfer here, utilized this quantum tunneling of magnetization. So now you have quantum effects directly as part of this molecule, not just the discrete energy levels, but actually quantum effect. Is that quantum nanoscience? Maybe. Right? But now there's no question. Hopefully Wolfgang will tell us about electrically driven nuclear spin resonance in single molecule magnets, a single molecule junction device that is coherently controlled. This is not the best data. I know you'll show us better data. Rabi oscillations and multi-qubit control of the nuclear spin states in this molecule. So you can see this research had a long-term goal, and that goal is quantum nanoscience. So all of this research is, by our definition, quantum nanoscience. because it is goal-oriented towards the core here. Now, in my own research field, as you know, I'm scanning tunneling microscopy. Well, I don't want to call myself an expert person. So, especially when you look at magnetic systems or spins, maybe you can start with the great work by Roland Wiesendanger and his team in Hamburg in Germany, where they looked at magnetic islands, and these islands, they switch as a function of their size. The magnetization can be stable or not, switch with temperature and size control. Definitely nanoscience, but no quantum coherence in the system. Then we found out that individual atoms on these surfaces can have discrete energy levels. We can see the spin states, the quantum states of these, so this is probably a step in that direction. But nowadays we can do coherent manipulation of these spin states, such as the Rabi oscillations here measured on a single titanium atom on a thin insulating film. Right? So this again is a progression where I believe that we can go towards the goal of quantum nanoscience, and we can make our way into the center of this field. Now I want to give you two more examples because they're a little bit, they were discussed by us and they were not as clearly cut as the ones I show you here. First one, Josephson junction based quantum computing, right? It's definitely quantum. It is one of the most quantum things we have nowadays because we want to use it for quantum computing. Superconducting quantum computing with 5 qubits is on the web. You can use it yourself. 50 qubits are in the labs. I don't want to talk about the quantum supremacy that is maybe or maybe not happening at this point. But clearly, quantum is not a question in there. But really here the question is it nanoscience? Right? Some of these devices here, this is a slide made by William Oliver, who's going to speak next. Some of these parts are very big. I can't read it myself here, something like tens of micrometers. So we wouldn't call that nanoscience probably. But some components are on the nanoscale. And what he points out, which I really like, is maybe we should include this in quantum nanoscience because the quantum coherence, the limits on the quantum coherence, they are in a large part governed by defects, atomic scale defects. And so understanding those defects will help to make better quantum coherence for these devices. So if you want to go to fault-tolerant Josephson junction-based quantum computing, you definitely need to understand the nanoscience in this part. Yeah. So you can argue either way. We decided to have it in. Let me give you another example. Ion trap systems. So here's taken from Wikipedia, magnesium atoms in an ion trap. There is no question that this stuff is quantum. This is really one of the beginning fields that started this whole quantum research, and there's a Nobel Prize given for it for its quantumness. For example, you can do global entangling gates here for 3 of these qubits or these ions. So here is a GHZ state entangling all 3 of them together, or you can choose to entangle 2 of them together. There's no question that they have an incredible amount of control over the quantum behavior, superposition, entanglement, and quantum coherence. But do they fall into quantum nanoscience? There we had some very heated discussions, I would say, and in the end we decided no. Why not? Because they don't call themselves nanoscience. Right? They would never think of themselves as part of the nanoscience community, so why should they be part of the quantum nanoscience community, which by definition is a subset of nanoscience? So we decided that these people would not be in, and so we don't have a session here on ion trap-based quantum computing. Okay, so that's the definition that we proposed, and maybe that's the second question. Do you agree with this definition? Do you think it is useful to have such a definition? And if so, do you think that this quantum coherent functionality at the core is a good idea to bring a community together and to develop tools from each other and synergy effects? We believe that's the case, but I think it's a hopefully in the coffee sessions and throughout this conference we can have some discussion about this. That's the quantum coherent functionality at the core of what we believe is quantum nanoscience. Okay, so then I want to just give you 2 or 3 slides of the Center for Quantum Nanoscience, which we have here at Iowa Women's University. Go into the same slide. For us, the nanoscience component does not include lithographically defined materials, for example. We have quantum surface science, atoms and molecules on surfaces, on UHV clean surfaces. atomically precise assembly, for example, using the STM, and some smaller aspect of molecular nanoscience in there. So this is the nanoscience component. We have many experiments now with using quantum superposition. We definitely study quantum coherence for these systems. We don't really have any entanglement yet between multiple spins, and the quantum measurement, we really haven't focused on that either. So we are, of course, a subset of what is quantum nanoscience. We don't plan to cover all of nanoscience. We could never do this, right? But maybe in this area, our goal is to become a pioneer and the worldwide best place for that subset of quantum nanoscience. Okay, so the research teams that we have, the research that we conduct, is most of it right now is quantum properties of individual spins on surfaces. Could also be two if you put them together. So that's our work based on scanning tunneling microscopy. We have an ensemble averaging team doing surface science, ESR, and some X-ray techniques. We have a smaller component of combining optics with scanning probe microscopy and atomic force microscopy, an even smaller component of nitrogen vacancy center-based research, and then an even smaller component of theory, not because I don't like theory, but our fabulous postdoc is only alone in this field, and we need to grow this field, right? So this definitely needs to become bigger. This is just to give you an idea where our focus is and what kind of research we do. The materials that we study, as I said, we have a little bit of work on these NV centers, but also some other point defects in materials. Lots of it on scanning tunneling microscopy, spins on surfaces, and a little bit of an effort on tailoring magnetic molecules for interesting quantum coherent spin properties. We use the discreteness of these systems, so we don't study continuous magnetism like thin films. We only study those things that have discrete energy levels to have any chance to go into quantum nanoscience. We then use quite a bit of CW, electron spin resonance, and also pulsed electron spin resonance. These are Wikipedia and Andrews papers, so not our own data, to study these quantum effects in the quantum nanoscience area. So our main tools, the main tool that we really use is scanning tunneling microscopy. About half the group is working, or maybe more, on scanning tunneling microscopy. We have a smaller effort on atomic force microscopy because we realize that having these conduction electrons nearby is a long-term problem for us. And one of the ways to get out of this is to have no conduction electrons. Hence, we need to use atomic force microscopy. We have one effort using a surface science quality electron spin resonance technique. We utilize external facilities such as the Pohang synchrotron facility and other synchrotrons to study some of the properties of spins on surfaces. And we have some optics component in our center. So, I'm almost finished. So here's a little movie on the construction of our building. That's our public relations slogan, engineering the quantum future. And you will have a chance to go to this facility tonight, this afternoon at 4 o'clock. We all move up there. We have lab tours for those of you interested to see the labs. And we also have refreshments and discussions up at our center. Here's a picture taken just Monday, a couple days ago, of essentially everybody in the center, almost everybody. We have postdoc positions available for those of you who are interested in working in quantum nanoscience, and that means using quantum coherent functionality of most of us spins on surfaces. But if you have other ideas that fall into this realm, you're very welcome to join our team here at EWA. And with this, I would like to thank you and welcome you again.